Hi, welcome to General Chemistry 151 at Johnston Community College. Today we'll be covering Chapter 1, Chemistry, the Central Science. We'll be working out of Chemistry, the 4th edition textbook by Julia Burdge and McGraw-Hill Education. So let's jump right in. First of all, a note about how these lectures will work. The PowerPoint presentations in their entirety are available on any time at Blackboard, and you can download them and print them or make notes on them, whatever suits your studying style best. For the purposes of these lecture videos, however, I am not going to go through every single slide because many of these slides are definitions and it would make the video much too long and be kind of a waste of our time. So I'm going to focus instead on the concepts that are trickier than just definitions, applying definitions, and the math, especially focusing on the math in chemistry. Chemistry is a quantitative science, so there's a lot of math involved. So mostly I'll be focusing on those kinds of problems rather than the definitions. So this lecture is easiest if you've at least read through the chapter, at least skimmed through the definitions is the main thing. You don't actually have to sit there and read word for word and comprehend the chapter in order to follow along with this lecture, but it does help if you at least know what the chapter is about, since I'll be skipping over a lot of the definitions. So, Chapter 1 has 6 individual sections. We'll be skipping over the first two, the study of chemistry and the classification of matter, since that is pretty much just definitions. So we will be covering today scientific measurement, section 3. Specifically, we'll be looking at the different systems of units that we use and how to calculate density. Properties of matter, we'll be focusing on how to apply those definitions to determine if things are chemical or physical properties, intensive or extensive properties. Uncertainty in measurement. This is significant figures, and where do we round when we are doing some sort of a quantitative problem? And using units and solving problems. This is mostly going to be unit conversions and how do we solve a problem that involves units. A huge part of general chemistry is the units. If you have a good grasp of the units, then most of the math problems will come fairly easily to you, which is why it's so important to focus on unit conversions if you are not already very good at unit conversions. If the math in this chapter is troubling you, please reach out to me. There's also an excellent tutorial of the math on Blackboard under Math Tutorials tab. And feel free at any point in time to email me or call or come by during my office hours, and I'd be happy to sit down and work with you in more detail with any of these problems. So let's jump into section 3, scientific measurement. So first of all, the base SI units that we use. Here in the United States, of course, we use the system that has things like pounds and ounces and cups and gallons, but that's not the system that the majority of the world uses, and it's certainly not the system that the scientific community uses. Scientific community in most of the world, of course, uses the metric system, which most of us who grew up here in the United States may not be very comfortable with the metric system, aside from buying a 2-liter of soda at the grocery store. Beyond that, we might not be quite as familiar with it. So let's first go over what are the base SI units for each kind of measurement we can make. So the base SI unit in metric for length is a meter, given the symbol m. Mass, this is a tricky one. Most people assume that the base SI unit for mass is gram, but it's actually a kilogram, or 1,000 grams, kg, is the base SI unit for mass. Time is a second. Current, which we will not deal with in Chem 151, but we will see that again in 152, is an amp. Temperature is not in degrees Celsius, it is in Kelvin. Amount of a substance, when we're dealing with amounts, is in moles. We'll deal with that more in Chapter 3. And then luminous intensity we don't deal with much in general chemistry. So with the metric system, as you saw with grams versus kilograms, they deal with prefixes and they're all in units of 10. which is why it's so easy to convert around the metric system once you're in the metric system. Unlike the standard system, where we could have, there's so many 12 inches in a foot, 3 feet in a yard, and there's no set amount difference in between the units as you're moving along. Whereas in the metric system, it's always something to a power of 10. And here in table 1.3, by the way, these tables come, every table and image you see in these slides are going to come straight out of your textbook. So if you're following along in section 3 of your textbook, you will see this table, so you could bookmark it for later reference. Shows you what these prefixes mean. So a kilo, I mentioned earlier that a kilogram is 1,000 grams. So here it says kilo is 10 to the third, or 1,000. Notice this is in scientific measurement here. We use this a lot because in chemistry we deal with very, very big numbers, like how many atoms are in a balloon of oxygen, or very, very small numbers, like how many grams does one atom of oxygen weigh. So we have to use scientific notation to denote these very big and very small numbers. If you are unfamiliar with scientific notation, there is a tutorial for it also on Blackboard under the Math Tutorials page. There's also Appendix 1 at the very end of your textbook is the math appendix, and goes over all of the math that you're expected to have a grasp of in order to move forward with the chemistry concepts in this class. So kilo is 1,000, or 10 to the third. 10 to the negative third, or 1,000th, or 1 over 1,000 is milli. So using this chart, you can convert in between units. And we'll see this later when we get to the last section of the chapter and actually do some unit conversions. So mass. Mass is not the same as weight. Mass is a measure of the amount of matter in an object or a sample. Weight, which we will not be using in chemistry, is how our mass relates to gravity, which is why they say you don't weigh the same here that you do on, say, Mars, because Mars has different gravity. But the amount of matter is constant regardless of the gravity. Temperature scales. Now, in chemistry, we don't use the Fahrenheit scale. There's a lot of problems with the Fahrenheit scale that I won't go into, but which is why almost no one uses the Fahrenheit scale except for the United States and maybe a few other small countries, but most of the world uses Celsius. Now, degrees Celsius is what we see the most often in chemistry, but it's not the base SI unit for temperature because it has a problem. Celsius can be positive or negative. So negative 20 degrees Celsius and positive 20 degrees Celsius are obviously very different temperatures. But if we're doing a calculation with it, say we're multiplying by temperature for some reason, in both cases we would multiply by a factor of 20, and that can be problematic. So we have a different temperature scale that we use called the Kelvin scale. This is the absolute temperature scale because it cannot be negative. The lowest possible temperature is 0 Kelvin, referred to as absolute 0. To convert from Kelvin to Celsius, the factor is 273.15, and you typically just take whatever your degrees Celsius are and add 273.15. So for example, if you had a temperature of 25 degrees Celsius, which is often considered room temperature approximately, you add 273.15, and this would give you a temperature of 298.15, and this is in Kelvin. Not degrees Kelvin, but simply Kelvin, which is an uppercase K. And this is the base SI unit for temperature. Now, if you're first given Fahrenheit, you'll first have to convert to Fahrenheit. And if you are unfamiliar with converting between Celsius and Fahrenheit, your textbook does an excellent job of going over how to do that. But we're going to move on to the more chemistry-specific conversions. So, normal human body temperature can range over the course of the day from about 36 degrees Celsius in the early morning to about 37 degrees Celsius in the afternoon. Express these two temperatures and the range that they span using the Kelvin scale. Notice that this is boxed in red and says sample problem 1.1. If you're following along with your textbook, sample problem 1.1 is shown in your textbook in Chapter 1. Now, you can follow along. It's the same solution. At the end of sample problem 1.1, however, in your textbook that is not in the slides, there are sample problems or practice problems, A, B, and C. Please focus on sample problem A and B after, or practice problem A and B after every sample problem. These are the problems that I look at when I'm doing your homework and I'm doing your tests and I'm making this. These are the kind of questions that I expect you to know how to do, how to calculate. Practice problem A is almost exactly like a sample problem for any of these sample problems in the textbook, just maybe with the numbers changed or maybe the chemicals changed when we get later on in the chapters. Sample problem B, on the other hand, is usually a similar problem but worked in reverse. So when we get to the density problems and it says, given this mass and volume, calculate the density, sample problem B, or practice problem B, may be the reverse. Given the density and the mass, go backwards and find the volume. So focus on being able to do both of those problems. So if you would like to, working along with the textbook, pause the video after the sample problem and go ahead and work out those two practice problems. The answers to the practice problems are in the back of the chapter, not the very back of the book, but the back of the chapter, unless you're, of course, using the e-book, in which case the solutions to the practice problems, you just hover over the question and it'll give you the solution there. So, moving on with this problem, it wants us to convert 36 degrees Celsius and 37 degrees Celsius in Kelvin. It also wants the range, meaning how much do they differ. So to convert, we just add 273.15, and we'll see that, and they rounded using significant figures. We'll talk about that later, why they didn't leave on the 0.15. And they get 309 Kelvin for the first temperature and 310 for the second temperature. These two differ by 1 unit or 1 Kelvin. As you'll notice, our original degree Celsius also differed by 1 degree Celsius. So the range is the same for both Celsius and Kelvin scales. On the other hand, Fahrenheit range is not equivalent to the range of 1 for a Celsius, which is why we don't use Fahrenheit very often. All right, so I mentioned units, SI units. Notice you saw one for length, you saw one for mass. You did not see one for volume. That's because volume is actually a derived unit. When we first learned about volume way back in elementary school, you learned about it probably in terms of geometry. You had, say, a cube, and you wanted to know what the volume of this cube was. And we found that volume is length times width times height. So if I have a cube, you'll have to bear with me with my drawing skills here. I have some sort of a length, some sort of a width, and some sort of a height to this. And my volume was length times width times height. Now, all of these are measured, if I was measuring this with a ruler, so they're all technically lengths. The height is just the length of the vertical. The width is the length of this side. So these are all lengths. The base SI unit for length is a meter. So a meter times a meter times a meter would give us a meter cubed. And this is the derived, because it's derived from base SI units, derived unit for volume is a meter cubed. However, this isn't very practical in most laboratory settings. I mean, if you think about how long a meter is, picture a meter stick in your head. It's a little bit longer than a yardstick. And then picture say a packing box that is a meter long, a meter wide, and a meter high. That's a huge box. That's not very practical volume to use in laboratory settings because we tend to not fill up boxes of that size with chemicals. So this is, even though it's the base SI unit, it is not the practical unit you most commonly will see in laboratory exercises. The more commonly used, you'll see, is the liter. Now, 1 liter is a cubic decimeter. So a deci means 1/10, or 1/10. If this was a decimeter, that would be 1/10 of a meter. So picture a meter and divide it in 10, and this is the length here. So if I take a cube that is 1 decimeter in height, width, and length, that would give me a liter. So 1 liter is equal to a decimeter cubed. Now if I took 1/10 of a decimeter, that would give me a centimeter, or 1/100th of the whole meter. 1/10 of a tenth is 1 centa, or 1 centimeter. Here, 1 centimeter is equal to 1 milliliter. 1 centimeter cubed, sorry, is equal to 1 milliliter. So the big takeaway here is that 1 liter is equal to 1 decimeter cubed, and 1 milliliter is equal to 1 centimeter cubed. So these conversions, you'll see these units used interchangeably. If you've ever worked in the medical field, or you're filling up a syringe or volume, you might have seen the volume cc. Say, you know, the patient needs 10 cc's of a drug. cc stands for cubic centimeter. So this is the same thing. A cc and a cubic centimeter and a milliliter are all actually the exact same unit. Density is also a derived unit. Density is the ratio of mass to volume. So here's an equation. Density is equal to mass over volume. Notice it is highlighted in yellow. Whenever we have a formula highlighted in yellow, if you refer back to your textbook, you'll see that this is also listed in your textbook as a formula, and at the end of the chapter it has a list of all the formulas that were noted in your textbook and highlighted. So the density formula, we can use units of grams for the mass and milliliters for the volume. And this is typically the unit you'll see when we're dealing with liquids, is grams per milliliter. It is the same as a gram per centimeter cube, since earlier we said centimeters cubed, milliliters the same. Just this is the unit we typically use with solids, since solids are typically measured using their length, width, and height. Now, gases are far less dense than solids or liquids. That's why, you know, air tends to float above, liquids and solids tend to sink down. So instead of using grams per milliliter, we typically use grams per liter when we're measuring the density of a gas. So let's do a little problem here. Ice cubes float in a glass of water because solid water is less dense than liquid water. That's pretty unique. Most solids are more dense than the liquids of their same state. The question asked us to calculate the density of ice given that at 0 degrees Celsius, a cube that is 2 centimeters on each side has a mass of 7.36 grams. So let's look at A first. Now, hardest part of chemistry probably is not the math, because the math in this is very rarely going to go anything higher than basic algebra, really. It's looking at a word problem and picking out the word problem, figuring out what numbers are pertinent, are they in the right units, what formula do I need to use, where does it go in the formula. Once everything's in the formula, then solving it's usually pretty easy. So let's looking at this word problem. We're given 3 numbers here. We're given a temperature, 0 degrees Celsius. We're given a length, 2 centimeters, length of a cube, and we're given a mass, grams, and we're asked for the density. Now, when you see the word density, it helps to go ahead and real quickly write what is the formula for density. Well, the formula for density is equal to mass divided by volume. So I need a mass. Was I given a mass? Yes, I was given a mass, 7.36 grams. So we know that's what goes right there, is 7.36 grams. But we need a volume. We're not given a volume, but we are given that is a cube that is 2 centimeters on each side. Now, we learned a long time ago, hopefully, how to find the volume of a cube from its length. Length times width times height, and then by definition, a cube is the same on all sides, so length, width, and height are each 2 centimeters. So the volume of this cube would be 2 centimeters for our length times 2 centimeters times 2 centimeters, length times width times height. So 2 times 2 is 4 times 2 is 8. So we'll get 8. Now, here's another trick that I see students messing up on is they multiply or divide, or whatever they're doing here, the numbers, but they don't change the unit. The unit is also being multiplied here. Centimeters times centimeters times centimeters. So that centimeters cubed is our unit here. So that would be our volume, what goes on the bottom here. So we have 7.36 grams on the top and 8 cubic centimeters on the bottom. So dividing these two numbers here will give us 0.092 grams per centimeter cubed, which is the same as a gram per milliliter. So that's part A. Part B then asks us to, using that density, determine the volume occupied by 23 grams of ice, still at 0 degrees Celsius. Notice we never actually used 0 degrees Celsius in the first problem. Sometimes there's numbers that are given there that are given for your information. Now in this case, the reason they specify is because density varies with temperature. The lower the temperature, that could change the density. So it's specified, but it's not actually used in our calculation. So just because a number is given a problem does not necessarily mean it has to go into your calculation. In this case, the temperature did not go into our calculation. So don't be alarmed if you see numbers that end up not actually going into your calculation. So this asks for the volume. Determine the volume given this mass and ice at 0 degrees Celsius, which means given the density, using the density we just calculated. So we're looking for volume, which means we need to rearrange our formula. Density is equal to mass over volume, and we need to rearrange it to solve for the volume. So if I rearrange it, I will get the volume is equal to the mass divided by the density. So rearranging simple equations is a skill you should have learned in early algebra. If you're having trouble with it, again, go to the Math Tutorials tab on Blackboard, and there's an excellent tutorial there on rearranging formulas that will help you with this. So we take the mass given, 23 grams, divided by the density we calculate in part A, and we will get 25. Now let's look at the units. For part A, the unit was gram on the top, centimeter cubed on the bottom, so we end up with a unit of gram per centimeter cubed. Here, our unit is gram on the top, gram per centimeter cubed on the bottom. Now, you should have learned early on, if we have a fraction that has the same thing on the top and the bottom, then those two things will cancel out. So grams in this case, the same on the top and the bottom, it cancels out. Centimeter cubed, it's on the bottom of a fraction here. Dividing by a fraction is the same thing as multiplying by its reciprocal, which means the centimeter cube will come up to the numerator, come out of the denominator and come to the numerator, because I'm dividing by 1 over it, which is the same thing as multiplying by it. So 25 centimeter cubed or 25 milliliters is the answer to part B here. And this is how to calculate density and calculate volume, or you could also do the same thing, solve for mass using the same equation. So that's it for section 3. Moving on to section 4. Section 4 doesn't have any math. This is physical properties, chemical properties, and intensive and extensive properties. Now, you may be probably already familiar with the terms quantitative and qualitative. Quantitative meaning dealing with numbers, but physical and chemical you may not be quite as familiar with. So a chemical property is one that deals with chemical changes. Chemical changes are ones that change the identity of the substance. Whereas physical properties do not change the identity of the substance. Physical changes pretty much are things like just changing the state of matter, going from a solid to a liquid, aka melting. If I had solid ice, which we know is ice, or solid water, ice, and I melted it, it became liquid water, but it is still water. Water is H2O. I did not change it. It's still H2O, whether it is a solid or a liquid. Melting it did not change the identity of that compound. Therefore, melting is a physical change, and properties dependent on that, such as melting point, the temperature at which water will melt, is a physical property. Chemical properties are ones that are a chemical change. They change the identity. such as if I had a piece of paper and I wanted to measure the temperature at which it will combust or burn. I can do that by heating up the paper until it catches fire and burns and measuring at what temperature it did that. That would be its combustion point. But at the end of that process, I no longer have paper. The paper has been chemically changed into a different compound. So combustion would be a chemical property, and the combustion point would be a chemical property, and combustion would be a chemical change. Extensive versus intensive properties. Extensive property are ones that depend on the amount of matter, whereas intensive do not depend on the amount of matter. I picture a glass of water, and I pour half of the water out. Any property of that water that changed because I poured half of it out would be extensive, whereas any property that did not change would be intensive. So I pour half of it out, things that change. Mass would change, certainly. I would have less mass of water. Volume would change. The volume of the water would decrease after I poured it out. Now, things that would not change, density. Water at about room temperature has a density of about 1 gram per milliliter. It doesn't matter if I have a cup of water or a gallon of water or a milliliter of water. Its density is intensive. It does not depend on how much water I have. Temperature. If I took the temperature of that glass of water and then I poured half of it out and took the temperature again, the temperature would not have changed. So that's another example of an intensive property. So to determine between extensive and intensive, just picture what changes if I were to remove some of my substance, and those are my extensive properties. Let's move on to significant figures next. Significant figures and knowing where to round. First, let's talk about exact versus inexact, the term exact numbers and inexact numbers. An exact number is a number that has limitless, it has no error. There's no error, and it has no sense of, okay, well, I'm only significant out to a certain number of digits. Exact numbers come about two different ways. From defined values, such as 1 inch is defined as 2.54 centimeters. This is the definition of an inch, 2.54 centimeters. So 2.54 is an exact number. We also have the defined numbers in the prefixes, such as kilo means 1,000. This number 1,000 grams per kilogram, when I'm using 1,000 in terms of how many grams in a kilogram, that is a defined value. So it's an exact number. You can also get exact numbers from counting whole objects. If I were to count out 12 marbles, I have exactly 12 marbles. There's no possible amount of error there. I don't possibly have 12.01 marbles or maybe 11.99 marbles. I'm counting whole objects, so I have exactly 12 objects. So those are the two ways of getting an exact number. And exact numbers have limitless significant figures in them. Any other method than counting whole objects are inexact numbers. So if I measure the length of something using a ruler, or I put an object onto a balance and measure its mass, or I use a stopwatch to measure how long it takes a marble to hit the ground when I drop it, those are all ways of measuring, and those will all yield inexact measurements. Now, even if you're not the one doing the measurement, there's still, if they were measured, they are going to be inexact. For example, if I said, okay, there are 365 days in a year. Well, how do we know that? Is a year defined as 365 days? No, actually a year is defined as the length of time it takes for a specific occurrence to be completed. In the case of here on planet Earth, 1 year is how long it takes the Earth to revolve around the sun. Now, that takes really 365 point some decimals amount of time for the Earth to revolve around the sun one time, but no matter how many decimals out you go, that was still measured. At some point in time, some scientist measured how long it took for the Earth to complete one orbit around the sun. So that was a measurement, not a definition. So that would be an inexact number. However, 1 hour is not measured as 60 minutes. It is defined as 60 minutes. So this is where I see students getting confused the most. Between exact and inexact numbers is with time. Time can be defined or it can be measured. Definitions of time are 60 seconds in 1 minute, 60 minutes in 1 hour. However, if time is defined rather by a measurement, such as a day is how long it takes for the Earth to rotate on its axis, that's about 24 hours, but that's actually a measured value, not a defined value. So whether or not time is defined by its measurement or defined by an occurrence like the Earth rotating or the Earth orbiting around the sun will tell you whether or not it's an exact, such as 60 seconds in a minute, or an inexact, such as 24 hours in 1 day. So once you've determined that you have an inexact number, say you are the one who took the measurement, how do I know how many of those numbers to record and consider significant? Significant figures are the meaningful digits in any reported number. Let's say I am measuring the length of this flash disk here, and I have two different rulers. Both of these rulers are measuring in metric. They're both measuring in centimeters, but the graduations are different. The first ruler has a graduation for every whole number centimeter. The second one has a graduation for every 1/10 of a centimeter. If I count, there will be 10 tick marks in between the 1 centimeter and the 2 centimeters. So every 1/10 of a centimeter, or 0.1 centimeter, has a graduation. So how do I know where to measure? The rule is you always estimate one more digit than you have a graduation for. So let's say I'm taking a measurement using the top number here. The top ruler, I have a graduation for every whole number centimeter, and the flash drive is definitely at least 2 centimeters. So that 2 is not estimated. Now, I do not have a graduation for a 1/10 of a centimeter up here, but I can estimate it. I can look here and go, okay, I'm about halfway in between the 2 and the 3. So I'm going to estimate the 10th place. I'm going to estimate this. This is my estimated or uncertain digit. Uncertain digit. Sorry, the pen's wanting to go everywhere, all over the page here. So the uncertain digit. Now here is the trick that a lot of students get confused with. They think that because this was estimated as an uncertain digit, it is not significant, and that is not true. This is still a meaningful digit. So even though it's the uncertain, the estimated digit, it is still significant. So if I were to look at this number, I would say that this number, 2.5, got to have a unit, centimeters, has 2 significant figures. I'm going to shorthand significant figures as sig figs, significant figure. All right. Now, say instead I measure the exact same flash drive using this ruler down here that has a graduation for every 1/10. Now, let's see. The 2, definitely at least 2 centimeters long, so we've got the 2. Now, the first place after the decimal, the 10th place, I have a tick mark for that. Let's see. I've got 2.1, 2.2, 2.3, 2.4. It doesn't look like it quite reached the 2.5, but I've definitely at least hit the 4. So that 4 is going to be a certain digit. But I can't just say, okay, 2.4 because I didn't estimate anything. That 4 was not estimated. There was a graduation for it. You must have when you're taking a measurement, and take note of this because when you're doing this in lab exercises, I'm looking for the number of digits you have in your measurements, and I know what in your lab kit, what the graduations are of your ruler and your graduated cylinders and such. So make sure you're recording the correct number of digits here. So I'm going to have to estimate. Now looking at this, it didn't quite hit the 5, but it's pretty close. So I'm going to estimate, say, 8, pretty close there. I'm going to estimate the 100th place as an 8 here. Now, your estimated digit and my estimated digit might be a little different. You might look at that and say, oh, that's definitely 9. And your friend might look at it and say, oh, that's definitely 7. But that's fine. There is some level of error in here. That's fine. That does not mean it is not significant. You are the person taking the measurement. So you made this estimation. You made this judgment call. That means it is significant. It is uncertain. There is some possible level of error in there, but it is still significant. So 2.48 centimeters, and this would have 1, 2, 3 sig figs, significant figures. So the number of significant figures in these numbers depend on what instrument was used to take that measurement. So what if I'm just looking at a number that's already been reported for me? How do I tell how many significant figures are there? Well, we have rules to determine that. The first rule is pretty easy. If I have any number, say 112.1, any number that is not 0 is always significant. So I would have 1, 2, 3, 4 significant figures in this number. Rest of the rules deal with what if it is a 0. When are zeros significant and when are they not? Sometimes zeros are significant, sometimes they aren't. So pay attention to the rules to determine. The first rule says that zeros located between non-zero digits, so in the middle somewhere, sandwiched between non-zeros, are significant. So 305, this 0 is sandwiched between non-zero digits, so it counts as a significant digit. So I would have 1, 2, 3 significant figures. 50.08, these two zeros are sandwiched between, they are significant. 1, 2, 3, 4 significant figures. All right. Zeros to the left of the first non-zero digit are not significant under any circumstances. These are actually just placeholders. So 0.0023, these 3 zeros do not count as significant figures. So I only have 2 significant figures. 0.000001 has just 1 significant figure. Now the reason why these are not significant figures, as I said, they're just placeholders. What does that mean? That means if I were to rewrite these in scientific notation, those zeros would disappear. So let's try this real quick. Let's rewrite 0.0023 in scientific notation. So that means we move the decimal until there is 1 non-zero to the left here. So I had to move this decimal 1, 2, 3 times. So I'm going to rewrite this as 2.3 times 10, and because I had to move it 3 times, -3. Notice now that it's written in scientific notation, and we agree, if we understand scientific notation, these are the same amounts. This is the same number. But it's clear when I wrote it this way, there are only 2 significant figures there. That's why zeros to the left never count. It's because when you write in scientific notation, they disappear. They're just placeholders. All right, so what if the 0 is to the right? Here's where the rules split again. Zeros to the right of the last, so on the end, are significant if the number contains a decimal point. Now it does not matter where this decimal point is. It does not have to be on the end. It can be anywhere there. If there's a decimal anywhere, we get to count the zeros on the end. So 1.200, because I have a decimal, those zeros get to count. So 1, 2, 3, 4 significant figures. What if there's no decimal place? Well, then it's ambiguous. You don't know. 100, for example, may have 1, 2, or 3 significant figures. It's impossible to tell without being given more information. So whoever wrote that number, took that measurement, should have given you more information. Say you are the one taking the measurement and you want to show that this number has, say, just 2 significant figures. How can you do that? Well, that's where scientific notation comes into play. So if they're ending at the 0 and you don't have a decimal, use scientific notation so you can put a decimal in there. So for example, if I had the number 130, if I wanted to show this number 130 had only 2 significant figures, I would write in scientific notation as 1.3 times 10 to the second. If I wanted to show that it had 3 significant figures, I would write it as 1.30 times 10 to the second. Now we see that all 3 digits are significant. So let's go ahead and count significant figures for a couple of examples here. Determine the number of significant figures in the following measurements. 443 centimeters. Well, that's pretty easy. 1, 2, 3 significant figures. 15.03. This 0 is sandwiched in between, so it counts. 1, 2, 3, 4 significant figures. 0.0356 kilograms. These zeros are leading zeros, which means they do not count under any circumstances. So we're going to ignore them and skip straight to the first non-zero. 1, 2, 3. This number has 3 significant figures. 3.000 times 10 to the negative 7 liters. There is a decimal. This one's written scientific notation. There is a decimal, so these zeros on the end get to count. 1, 2, 3, 4. There are 4 significant figures in this number. 50 milliliters. Well, there's no decimal here, but there's a 0 on the end. We don't know. So I would say that E is ambiguous. It might have 1, it might have 2. We need more information to answer that question. For F, 0.9550 meters. The leading 0 doesn't count. Remember, leading zeros don't count. The 0 on the end, however, does get to count because there's a decimal. So I have 1, 2, 3, 4 significant figures in this measurement. Alright, now that we know how to count the number of significant figures, let's figure out how to round. So we're going to look at this first just with simple math problems, just leaving the chemistry out for a little bit here. So the rules for where to round differ depending on whether or not you are doing an addition-subtraction problem or a multiplication-division problem. Let's look at the first rule. The first rule is if you're doing an addition or subtraction. Now this actually has nothing to do with significant digits. Addition and subtraction, on the other hand, depends on where the decimal places are, how many decimal places there are. So the rule is that your final answer cannot have more digits to the right or on the end of the decimal point than the original number with the smallest number of digits to the right of the decimal point. So the easiest way to do this is, say for an addition or subtraction, let's line them up with the decimal place lining up and then count how many digits we have after the decimal. So this first number we have 2 digits after the decimal point. The second one we have 3 digits after the decimal point. So if I add this up, just plug my calculator, here's the answer I get. Now because I've got 2 digits versus 3 digits, the thing is you cannot have more than the original with the smallest number of digits, regardless of whether or not that's the smaller number. In this case, we have 2 digits in our first number and 3 digits in our second number, so we cannot have more than 2 digits in our final answer. So we take our final answer and we round it so it just has 2 digits. So this would round to 102.73. Same rule goes if you're subtracting here. So here we're subtracting. Our first number has 2 digits. Our second number has 1 digit after the decimal. So our final answer cannot have more than 1. Now here I have 123.19. I want to have just 1 decimal. This 1 will round up to 2 because the number following it is 5 or greater. So that is the rule for addition, subtraction. It has absolutely nothing to do with the number of significant figures. Multiplication, division, on the other hand, now it does matter how many significant figures you have. Rule's the same though, as far as you cannot have more digits than the smallest number of significant figures in any of your starting numbers. It's just instead of looking at the number of spots after the decimal, if there is one, we're looking at the number of significant figures. So in this number, my first number has 4 significant figures, my second number has my first number has 2 significant figures, my second number has 4 significant figures. So I cannot have more than 2 significant figures. So 2 versus 4, pick the smaller number, the smaller number of significant figures. which is 2 significant figures. So I need 2 significant figures. So 1, 2, leave off the rest. I just have 11 for that number. In this division, one of my numbers has 1, 2, 3, 4 significant figures. The other one has 1, 2, 3, 4, 5 significant figures. So 4 significant figures versus 5 significant figures, so our final answer cannot have more than 4 significant figures. Now, when I'm counting significant figures, remember, leading zeros do not count. So these first 2 zeros do not count. I want to count off 4 significant figures, so I'm going to go to the 3, because that's the first digit that is significant, and start counting there. So 1, 2, 3, 4. I round at that point. Now the number after the 2 is greater than 5, so that 2 will round up to 3. And there's my rounded number. So, to recap, if you're adding or subtracting, you round according to the fewest number of decimal places. If you're multiplying or dividing, you round according to the fewest number of significant figures. Now, what about that whole exact versus inexact number we talked about earlier? Exact numbers, I said, have no level of error, so they technically have, you could say, infinite number of significant figures. So, for example, if I had 3 objects that weighed 2.5 grams each, and I wanted to figure out the total mass, it would be 3 times 2.5. Because this 3 was 3 objects, or that is an exact number, we only round according to numbers that are inexact. So we would round to significant figures according to the second number, not the first number. So 7.5 has 2 significant figures. So this 3, because it was an exact number, has theoretically a limited number of significant figures when we're deciding how to round. Now, if you have multiple steps, those ones we saw all just had one step. We added, we subtracted, we multiplied, we divided. Just one step. What if you have multiple steps? Well, if you have multiple steps and you round every single step, then you're going to get something called rounding error. Rounding error is how much error there was when you dropped off the end of the number, when you rounded off. Now, if you do that just once at the end of the problem, then that's an acceptable amount of error that just is the price to pay to round. But if you do that at the end of every single step, then those little bits of error will start compounding on themselves to the point where it becomes one big error. Therefore, it is better to, when you're doing a multiple step process, keep at least one extra digit until the end and then round at the very end. Now, when I'm calculating something that has multiple steps, I use a calculator that allows me to store previous answers. And that way I don't have to round at all. I can keep all the digits and do it either in all one fell swoop or save them all and calculate with all of the digits in there. That's fine. You can do that. Or if you're the kind of a student who likes to write down your answer at the end of each step and then plug that into your calculator, that's fine. Just keep at least one extra digit than you know you. So if you know your final answer needs 4 significant figures, make sure at each step you're counting out 5 significant figures and then round for the very end. So, perform the following arithmetic operations and report the result to the proper number of significant figures. Now, this first number is an addition problem, so we're going to round according to the decimal places. So 1 decimal place here, 3 decimal places there, so our final answer needs just 1 decimal place. So the answer to A would be 317.5, which is the answer, or sorry, 318.2, which is rounded to just 1 decimal place. Our second problem there is a subtraction, so we're still going to go by decimal places. I have 2 decimal places and 3 decimal places, so I'm going to round to 2 decimal places. So subtract them, plug in the calculator, this is what we get. Rounding to just 2 decimal places, we'll keep the 7 and the 2, but the 2 rounds up because after it's 5, so 0.73. Now here we have an addition problem. Notice here when we were, a division problem. Notice here when we were adding, they had the same unit. That's kind of a universal rule. You cannot add or subtract things unless they are in the same unit. If I gave you a volume of 20 liters and I asked you to add 25 milliliters, you wouldn't say 20 plus 25. you would have to make sure they're in the same unit first before you can add them. The same rule does not apply for division, but it will change our unit. So we have 13.5 grams divided by 45.18 liters. This looks like a density equation. Grams divided by liters or mass divided by volume. So we're calculating the density of something. So our final unit will be grams over liters. So this is a division problem. So we're going to round according to the fewest number of significant figures. 13.5 has 3 significant figures. 45.18 has 4 significant figures. So we need just 3 significant figures. So do the division, get this whole long number in our calculator. Where do we cut it off? Cut it off according to 3 significant figures because that is the fewest number of significant figures of any of our starting numbers. Again, ignore leading zeros starting at the 2. 1, 2, 3. Round up to the 8. And since the number after 8 is 5 or greater, we're going to round it up to a 9. So 0.299 in our unit is gram per liter. Back to D, 6.25 centimeters times 1.175 centimeters. This is a multiplication, so we're going to go by significant figures. Centimeters times centimeters will give us centimeters to the second, or centimeters squared. Multiply them out. I've got 3 significant figures and 4 significant figures, so I'm going to round to 3 significant figures. So I get this long number in my calculator. I round to just 3 significant figures, so 1, 2, 3, round up to the 4, 7.34 centimeters squared. All right, looking at E, this is the one that is tricky. This is an addition problem, which means we're looking at the number of decimal places. But I said you have to be in the same unit. That, to add or subtract, that includes the same power if you have it written in scientific notation. This first number is times 10 to the power of 2. The second one is times 10 to the power of 3. We cannot add them until they're in the same unit, including the 10 power. So we could either take this number and put it to 10 to the third and move our decimal, or we could take this number and move our decimal this way and make this power of 2. So let's do that. Let's rewrite this problem, rewrite this number 4.991 times 10 to the third as 49.91 times 10 to the power of 2. Yes, this number is not correct scientific notation. Correct scientific notation will only have one digit before the decimal, but it will serve our purposes so we can simply add the numbers together. And now we can see I've got 2 spaces after the decimal here, 2 spaces after the decimal here. So after I add them, I will keep 2 spaces after the decimal. So add them together, 2 spaces after the decimal. Now, this again is not correct scientific notation. Correct scientific notation has just 1 digit before the decimal, so we're going to have to move that decimal back. So 5.537, and that will make that 10 to the second into a 10 to the third. So that was probably the only one that was really tricky. These were all single-step conversions, or single-step significant figure problems. Now let's kind of put in the chemistry a little bit. Let's look at a word problem. How we deal with this in a word problem. Sample problem 1.7 says an empty container with a volume of 9.850 times 10 to the second cubic centimeters is weighed and found to have a mass of 124.6 grams. It is filled with the gas and reweighed, and the new mass of both the container and the gas is 126.5 grams. Determine the density of the gas to the appropriate number of significant figures. Now remember, density is mass over volume. Gases, if you were reading earlier on in the chapter, properties of gases take on the entire volume of the container. Well, the volume of the container is 9.850 times 10 to the second cubic centimeters. So we know that the volume, V, is that 9.850 times 10 to the second cubic centimeters. But the question is, what is the mass? We want the density of the gas, which means we want the mass of just the gas. I have the mass of the container and the gas and the mass of just the container. So I need to do a subtraction here to get the mass of just the gas first. So there's 2 parts to this problem. The first one's going to be a subtraction, my filled container minus the empty container to get the mass of the gas. So that subtraction will go according to the number of decimal places. And then the second part's a division. So division then will go by the number of significant figures. So let's do the subtraction first. Do the subtraction first. 1.265 or 1.26.5 minus 124.6 gives us 1.9. Now we have one decimal place and one decimal place, so our final answer needs just one decimal place, 1.9. Now I would keep extra digits here if I needed them. I don't need them, but take note now that this number has two significant figures. So going into the second part of the problem, where we plug it into density as mass over volume, we're looking at a number with now two significant figures. So now this number has two significant figures. We're dividing by the volume, which has 1, 2, 3, 4 significant figures. So we're going to round according to two significant figures because that is a smaller number of significant figures. So take the number that our calculator gives us, round according to two significant figures, ignoring the leading zeros, starting with the 1, 2 significant figures, drop off the 3, 0.0019 gram per centimeter cubed, or written in scientific notation, 1.9 times 10 to the negative 3 gram per centimeter cubed. So that's how to round when you're dealing with a multi-step word problem. Most problems that you'll come across in this course, however, you can look at the numbers in your starting problem and go by the number of significant figures, since most of them deal more with multiplication division than subtraction. But for the purpose of this chapter, make sure you're paying attention to each step, how many significant figures there are. All right. Last section of the chapter is conversion factors, dimensional analysis to convert a measurement from one unit to another unit. Now this dimensional analysis, sometimes called factor label method, sounds fancy, but it just means I am multiplying by a factor that cancels the unit I started with and leaves me with the unit that I want. Now how does it cancel units? Well, if you have the same thing on the top and the bottom of a fraction, or you're multiplying by a fraction that has a unit opposite from where you started, those units will cancel out. For example, let's look at inches to centimeters. Here's a nice easy going from the standard to the metric. 1 inch is 2.54 centimeters. This is called my factor. Conversion factor. Now for a list of common conversion factors, you can certainly find them on the internet, print them off, but your textbook also has a list of them along with the end matter at the very end of the textbook. So we can take this, and since both sides are equal, we can write it as a fraction, and both of these fractions would be equal to 1. 1 inch and 2.54 centimeters is the same length, so this fraction is equal to 1. Or I could write it with the 2.54 centimeters on top and the 1 inch on the bottom. This fraction is still equal to 1. So which fraction do I pick to multiply by? Well, if I picked the first fraction, inches on top, centimeters on the bottom, then I could use that to cancel out centimeters, because centimeters on the bottom. But if I wanted to cancel out inches, I would need the second one. Let's see what that looks like. Say I wanted to convert 12 inches to centimeters. I'm starting with inches, which means I need one of these that has inches on the bottom. So I would pick the second one, the second factor. Inches is on the bottom, so inches will cancel. I'd multiply across the top, divide across the bottom, so 12 times 2.54 divided by 1 gives me 30.48 centimeters. Now, let's look at this. Depending on how you learned how to multiply fractions or convert units in a previous course, say in high school maybe, you may have seen this written using the railroad method, which means I'm going to draw a straight line, and starting with my starting amount in this case was 12 inches. And then I'm going to draw a vertical line for my first conversion. Now this one I'm only going to have one conversion, but this is a great method if you have multiple conversions. So whatever unit I start with, in this case it's inches, the unit you start with in your first track will drop to the bottom. So unit drops to the bottom, inch down to the bottom. The unit that you want will go then on the top if you have a direct conversion from the unit you started with to the unit you want. And yes, we do. We have a direct conversion from centimeters to inches. So centimeters will go on the top. Now, the numbers here come from my conversion factor. 1 is tied to inches, so I'm going to write a 1. 2.54 is tied to centimeters, so I'm going to write a 2.54 next to the centimeter. Now, if you had more conversions to do, we would keep on doing it on this line. When I have the same unit diagonal from each other, like the inches are here, they will cancel, and they do. There's nothing diagonal from centimeters, so it stays centimeters, which is good because that's the unit we wanted. We're going to multiply across everything at the top and divide by everything at the bottom. So 12 times 2.54 divided by 1 will give us our 30.48 centimeters. Now, rounding. 12.00 inches has 4 significant figures. How many significant figures in 2.54 centimeters? Trick question. 2.54 centimeters has infinite significant figures because it is the definition. So if it is the definition, it is an exact number, and we only deal with significant figures of inexact numbers. So we're just going to look at the 12, which has 4 significant figures. So we need 4 significant figures in our final answer, and we don't need to do any rounding. We're done. Now, if I wanted to take this a step further and say go all the way to meters, then I would add on one more factor here. And I could just do this by adding another railroad track if I wanted to. We're just going to write it here as another fraction. So 1 meter has 100 centimeters. That's another factor. 1 meter is 100 centimeters. So I would, starting with centimeters on the top, I would put it in the bottom. Meters on the top, 100 goes with the centimeters, 1 goes with the meters. Multiply across everything on the top, divide across everything on the bottom. So 12 times 2.54 times 1 divided by 1 and also divided by 100 gives us 0.3048. So dimensional analysis, we could keep on going as many times as we need. This is if we did not have a direct conversion from inches to meters, we would take a 2-step unit conversion. So let's try this out. The FDA recommends that dietary sodium intake be no more than 2,400 milligrams per day. What is the mass in pounds if 1 pound is equal to 453.6 grams? And it's asking us to assume the number 2,400 has 4 significant figures. So I guess this is a defined value for the FDA. So we're going to assume it has 4 significant figures. Let's just put a decimal there to remind us. So we have pounds to grams, but we're starting with milligrams. So we don't have a direct conversion from milligrams to pounds, but we do have a conversion from milligrams to grams. Milli means 1,000th, or there are 1,000 milligrams in every 1 gram. So there's my first conversion factor. So starting off with 2,400, I can use the first conversion factor to get to grams, and then I can use my second conversion factor, 1 pound is equal to 453.6 grams, to get to pounds. So how is that going to look? 2,400 milligrams, my first factor. Milligrams drops to the bottom, grams on top. 1 goes with grams, 1,000 is tied to milligrams. Now milligrams will cancel, and I'll be left at the end of the first step with grams. Let's keep going. Now grams is on top, it drops to the bottom. Pounds on top, that's the unit we want to end up with. 1 pound, 453.6 grams. So now grams will cancel, I'll be left with pounds, which was the unit I wanted, so I can stop. Multiply by everything on the top, so 2,400 times 1 times 1. Divide by everything on the bottom. Divided by 1,000 and divided by 453.6. Now be careful here. I see students sometimes typing this in their calculator. They'll type 2,400 divided by 1,000 times 453.6. And that's wrong, because the calculator thinks you divide by 1,000 and then multiply by 4,053.6. 453.6 is in the denominator, so this should not be a multiplication. This should also be a division. So make sure you're dividing by everything that's on the bottom. So keep on clicking divide, divide, divide. Alternatively, you could use parentheses if you want to, but just for simplicity's sake, it's easy to just write a divide instead. And so you get 0.0005291 pounds. We've got 4 significant figures, we were told, so we're going to ignore the zeros and keep 1, 2, 3, 4 pounds. 4 significant figures. Let's try another one. Now this one is tricky because the unit conversion is going to need a little bit of work before we can use it. This question says, an average adult has 5.2 liters of blood. What is the volume of blood in cubic meters? Now, I don't have a direct conversion from liters to cubic meters, but I do know that 1 liter is equal to 1 decimeter cubed. All right, well, a decimeter is 1/10 of a meter, so there are 10 decimeters in every 1 meter. So here's my factors. But you can't just jump straight into it because notice decimeter cubed is not the same as a decimeter. Decimeter cubed, decimeter, not the same. So it's not going to convert. Plus we want cubic meters. We want meters cubed. And this is not a meter cubed, this is just a meter. So when you're dealing with cubic or squared, this is a square, if you're dealing with cubic units, take your conversion factor and cube both sides. Remember, beginning of algebra, anything you do to one side, you must do unto the other. So if I cube one side, I'm going to have to cube the other side. Now the cube gets distributed to everything on that side. So 10 gets cubed, and so does decimeter. So 10 times 10 times 10 is 1,000. And then the unit also gets cubed, so decimeters cubed is equal to, now 1 cubed is still 1, 1 times 1 times 1 is still 1, meter cubed. So 1,000 decimeters cubed is equal to a meter cubed. Now they have it set up like they already knew the unit. I worked it out this way to show you if you didn't already know what that conversion factor was. So now that we have the conversion factors, it's just like the last problem. Our starting unit is liters, so our first factor, liter, drops to the bottom. And they had 1,000 centimeters cubed. We went to decimeters. That's fine. It's going to work out the same way. So 5.2. Let's work it out our way. 5.2 liters times our first one was 1 decimeter cubed is equal to 1 liter. Liters cancel. Second factor, 1 meter cubed is equal to 1,000 decimeters cubed. Decimeters cubed cancels. So I have 5.2 times 1 times 1 divided by 1 divided by 1,000. So 5.2 divided by 1,000, and our final unit will be meters cubed. It's the only thing that didn't cancel. Would give us 5.2 times 10 to the negative third. Once it's written in significant figures, meters cubed. So same answer. So that is how to use dimensional analysis to convert the units. The biggest mistake I see students making here is not writing the units. When I have students come to me saying, I don't know why my answer is being marked wrong, I think I did all the steps right, 9 times out of 10 I look at their work and the first thing I ask them is, well, where are all of your units? And they said, oh, I just thought about it in my head. Well, that's where the mistake was. If you don't write down the unit at every point in the process, you think you're saving yourself time, but it's not going to save you time when you make a mistake. Write down the units at every point in the process, keep track of them, cancel them as needed, and keep on doing that through the entire semester, and it'll cut down on a lot of frustration with wrong answers. So that is the end of Chapter 1. Go through all of the sample problems that we went over today in your textbook and work out the practice problems and make sure you can get to the right answer. And feel free to email me or contact me if you're having any trouble, and I'll see you again for Chapter 2.